This topic will introduce the scalar product of two vectors and look at how to use it to find the angle between those two vectors. Given points A and B with position vectors 3, 7 and 6, 2, we can find the angle between them, AOB. We could do this by plotting the 2 points, so point A and point B. We could calculate the side lengths. So the side lengths are just the magnitudes of the two vectors, so root 58 for OA and root 40 for OB. We could then calculate the vector from A to B and calculate its magnitude as well. And we could then use the cosine rule to find the angle that we need, AOB. So the cosine rule gives us an angle of 48.4. We're now going to look at an alternative way of finding this angle using the components of the two vectors. We're now going to do a more generalised calculation for angle AOB, this time with point A having position vector A1, A2 and point B having position vector B1, B2. So we're going to start by finding OA squared, so that's the magnitude of vector OA but then squared. So taking the components A1 and A2, we get A1 squared plus A2 squared. If we wanted just the magnitude of A on its own, we could then have square rooted this, but given that we're going to be using A squared in the calculation, we're going to leave it as OA squared for now. Similarly, for B, the vector OB has got a magnitude of B1 squared plus B2 squared, square rooted, so therefore OB squared can be written as B1 squared plus B2 squared. We can find vector AB by calculating OB minus OA. The components of that will be B1 minus A1, B2 minus A2. So AB squared is B1 minus A1 squared plus B2 minus A2 squared. I'm going to multiply that out. It's quite long at the minute, but quite a lot of that will cancel or simplify. I'm now going to use the cosine rule. So again, we're using this version of the cosine rule. So in terms of how the sides are labelled here, we're calling side A here, we're calling this side B, and we're calling this side C. So in terms of the cosine rule here, we also have the magnitudes A and B. So we can substitute in the values that we just found. So A squared is just going to be this vector here. B squared is just this here. And C squared is just going to be all of this here. We've then got 2AB, which we have called magnitude of A, magnitude of B on the bottom. So quite a lot of those terms on the numerator cancel, leaving us just with 2A1B1 plus 2A2B2 over 2 magnitude of A, magnitude of B. We can see that a factor of 2 will also cancel, leaving us with cos theta is A1 B1 plus A2 B2. So we can see the denominator is just the magnitude of the two vectors multiplied together. The numerator is something we're going to look at now. This is the scalar product of vectors A and B. The scalar product is one of the methods for multiplying vectors. When you find the scalar product of two vectors, the answer is always a scalar, hence the name scalar product. The symbol for the scalar product is a dot. So if you wanted to write the scalar product of A and B, we would write A dot B. For that reason, the scalar product is also sometimes informally called the dot product. The definition of the scalar product for two vectors A and B is that A dot B is the magnitude of A times the magnitude of B multiplied by cos of theta, where theta is the angle between A and B. This can be rearranged to give us cos theta equals A dot B over the magnitude of A times the magnitude of B. You'll recognise this from the previous example where we were finding the angle between A and B. In 2 dimensions, if we want to calculate the scalar product of A and B, if vector A is A1, A2, and vector B is B1, B2, then A dot B is found by multiplying the x components together, A1, B1, plus, and then multiplying the y components together, A2, B2. In 3 dimensions, this just continues to the 3rd component. So A dot B is A1 multiplied by B1 plus A2 multiplied by B2 plus A3 multiplied by B3. We're going to find the angle between each of these pairs of vectors using the formula that cos theta is the scalar product of A and B divided by the magnitude of A times the magnitude of B. So we've got 2 vectors in part A. I'm going to start by defining A as being -1, 5, and B as being 2, 3. We're then going to calculate each of the things in the formula. So A dot B will be 1 minus 1 multiplied by 2 plus 5 multiplied by 3. So that is -2 plus 15, which is 13. We're also going to find the magnitude of the 2 vectors. So the magnitude of A is -1 squared plus 5 squared, square root. So that gives us root 26. The magnitude of B is 2 squared plus 3 squared, square root, which is the square root of 13. So we've now got everything we need to substitute into the formula to find theta, the angle between them. So cos theta will be 13 over root 26 root 13. So therefore theta will be inverse cos of the value found there, which is 45 degrees. For part B, we have 2 vectors in 3 dimensions. You may find this easier to write the vectors as column vectors. So 3i minus 2j plus 4k can be written as 3 minus 2, 4. And 2i plus k can be written as 2, 0, 1. We can then perform the same calculation again. So A dot B is 3 times 2 plus -2 times 0 plus 4 times 1, which gives us 6 plus 4, which is 10. The magnitude of A can be found 3 squared plus -2 squared plus 4 squared, square root, which is root 29. Magnitude of B is 2 squared plus 0 squared plus 1 squared, square rooted, which is root 5. So using the formula, we get cos theta is 10 over root 29 root 5. So theta is the inverse cos of 10 over root 29 root 5, which to 1 decimal place is 33.9 degrees. The scalar product can also be used to show that 2 vectors are perpendicular, remembering that perpendicular vectors have an angle of 90 degrees. So here we're going to start by finding A dot B. So the scalar product of these two vectors are 3 times 10 plus -5 times 6. Remember, you can always convert these into column vectors if you prefer, or you can keep them in unit vector form. So here we get 0. So actually, when we're going to substitute 0 into the numerator of this formula, we don't actually need to calculate the magnitude of A or the magnitude of B, because this right-hand side here is going to become 0 because of the numerator being 0. So therefore, this is immediately simplified to cos theta equals 0. Therefore, we know that theta must be 90 degrees. We can actually conclude that for any two vectors, if the scalar product A dot B equals 0, the angle between them must be 90, so they must be perpendicular vectors. We're now going to try and find two possible values for A and B, such that the two vectors A minus 5B and 6, 2, 1 are perpendicular. We're going to use the fact that if A dot B equals 0, we can conclude that A and B are perpendicular vectors. So for this, we're going to calculate the scalar product of the two vectors. Here we get 6 times A. We then get minus 5 times 2, which is minus 10. And we get B times 1. And in order for two vectors to be perpendicular, the scalar product needs to be 0. So therefore, we have got that 6A plus B would equal 10. Because we were just being asked to find possible values of A and B, we can select any pair of A and B such that this equation is satisfied. So we could, for example, choose A equals 1, B equals 4. That would give us 6A plus B equals 10, and therefore we would end up with a scalar product of 0, so the two vectors will be perpendicular. Here we've been given 3 points, A, B and C, and asked to find the angle ABC. So for this, we need to first of all sketch the coordinates. They don't need to be in the right place. In fact, in 3 dimensions it'd be quite difficult to draw this. However, we do need some kind of sketch just to give us an idea of which vectors to use. So we're going to put A, B and C in a triangle as shown. We're going to identify the angle that we need is at B, so therefore we need to find the vectors from B to A and B to C. Remember that in order to find the angle between two vectors, they either need to both start at the same point or end at the same point. They either need to be both going out of B or both going into B. We've chosen two vectors that are coming out of B. So we need to find BA. BA is found by doing OA minus OB. And BC is found using OC minus OB. So we've now got those two vectors there. Remember that the coordinates of a point are also its position vectors. So that's how we calculated OA minus OB and OC minus OB. Now I'm going to find the scalar product, A dot B. The scalar product of these two vectors is 3. We're then going to use the formula. Cos theta is A dot B over the magnitude of A times the magnitude of B. So here we have A dot B is 3 on the top. The magnitude of A is 1 squared add minus 1 squared add 2 squared, square root. And the magnitude of B is 3 squared plus minus 2 squared plus minus 4 squared, square rooted. This simplifies down to 3 over root 6 root 29. If we find inverse cos of that, we will get the angle 76.9. So that is the angle between ABC. can also use the scalar product to find the angle between two lines. For this, we only need the direction vector of each line. This is because if we take two lines, take their direction vectors only, and find the angle between those two directions, the angle between the two direction vectors will be the same angle as the angle between the two original lines. This works even if the lines don't intersect. If the lines are skew, we can still find the angle that they would make. If the scalar product of the two direction vectors is negative, then we will end up with an obtuse angle between our two vectors. If we wanted the acute angle between the two lines, we could use the fact that 180 minus an obtuse angle gives us the required acute angle. This is because the obtuse angle and the acute angle together form a straight line. If two lines are parallel, then their direction vectors will be multiples of each other. Also, if two lines are parallel, the scalar product will equal the product of the two magnitudes. In other words, if we take two vectors A and B, where one is a scalar multiple of the other, then the value of A dot B will be the same as the value of the magnitude of A multiplied by the magnitude of B. This means that this fraction will always become 1, and since inverse cos of 1 is 0, that tells us that the angle between the two lines will be 0, so they must be parallel lines. You may like to check this fact by taking two parallel vectors and calculating A dot B over the magnitude of A times the magnitude of B, and verifying that we get the answer 1. Another rule which we have already seen is that if two lines are perpendicular, their scalar product will equal 0. If A dot B equals 0, you don't need to calculate the magnitudes of A or B, you can just conclude that the lines must be perpendicular, because inverse cos of 0 is 90. In each of these 4 questions, for each pair of lines, first of all, find a suitable direction vector for each line, then find the angle between each pair of lines. So for the first question, the first line has a gradient of 5. So a suitable direction vector could be 1, 5. For every 1 you travel in the x direction, you travel 5 in the y direction. The second line, the gradient is 2, so 1, 2 would be a suitable direction vector. So the calculation for the angle between the two lines gives us an angle of 15.3 degrees. For the second pair of lines, the gradient is 2 for the first line, so we could use 1, 2 as the direction vector. For the second line, we need to rearrange the equation to find the gradient of the line. We can see here that the gradient is -1/2. So a potential vector could be 1, -1/2. For every 1 you travel across, you travel 1/2 down. However, since only the direction matters, it may be simpler to use the vector 2 - 1 for this purpose. So using 1, 2 and 2, -1 as the two direction vectors, you can see in this case the scalar product is 0. This tells us that the angle between the two lines is 90 degrees. We can also verify this using a rule we've previously seen, that if the gradients are negative reciprocals, the lines will be perpendicular. For question 3, we need to find the direction vector of each line. First line has a direction vector 4, 2, 6, found by reading the denominators of the fractions. You could simplify this down to 2, 1, 3, if you preferred. And then for the second line, we're going to use -2, 1, -3. So the calculation again for the angle between these gives us 180 degrees as the angle between the two lines. Finally, for the fourth pair, we can see the first line has a direction of 3, 4, -2 by reading the denominators of each fraction. And for the second one, we can see that the direction in the x component of the direction vector is 4. The z component is 6. And because the equation just uses y equals 6, that tells us that the direction is 0 in the y direction. So 4, 0, 6 is a potential direction vector. We could simplify this down to 2, 0, 3. We can then find the angle between those two lines using the formula. Again, we get a scalar product of 0, leading us to an angle of 90 degrees. So from this, we can conclude that in question 2, the lines are perpendicular. In question 3, the lines are parallel but travelling in opposite directions. So the angle is 180 between the two lines. And in question 4, we can conclude that the lines are perpendicular as well. Now complete questions 1 to 11 of exercise 9D on page 216.